Hello everyone. So, I welcome you all again for the second lecture on electromagnetic induction. I am Sameer Lavankar. So, let us start our lecture. So, as previously stated, this was our course line. In the last lecture, we already completed with the introduction of electromagnetic induction, followed by the experiments of Faraday and Henry. To brief you out about the last lecture, there were 3 experiments which I talked about. Experiment number 1, in which there was a bar magnet plus a coil. Let me denote coil by C1 only here. Then there was a second experiment in which there were 2 coils. Let me denote it by C1 and C2. And the third experiment also comprised of 2 coils, but with one coil having a tapping key. So, these were the 3 experiments we talked about in the last lecture. Today we will start with magnetic flux. If you remember correctly, in the last lecture I talked about something like, let us say these are 2 points A and B, and let us consider an imaginary rope here. For example, not to be imaginary rope here, let us consider a rope here. So, when the magnetic or the magnetic effects come into picture, 0 units was converted into 5 units, 5 units was directly converted to 500 units when an iron nail was inserted into the magnetic field. So, what are these units talked about here? What is this units here? What is the thing is how we define, how we use, how we collaborate with the idea of magnetic induction. Electromagnetic induction to be precise will be talked about in magnetic flux, followed by Faraday's law of induction and so on. So, for now, just to have an idea, introduction is done and experiments of Faraday and Henry are done. So, what is magnetic flux? Let me start with magnetic flux. So, before we state and appreciate his laws refer to here Faraday. So, before we state and appreciate his laws, I am sorry for this mistake, it should be Faraday here. Faraday was a scientist. Before we state and appreciate Faraday's laws, we must get familiar with the notion of magnetic flux phi b. So, here the denotation is phi b. So, please be clear of this statement that to denote magnetic flux we use the symbol of phi. Magnetic flux through a plane of area A. So, please so now the figure to be ascertained here should be the right one. So, magnetic flux through a plane of area A. Here the area A is the planar area, of the square. If we are seeing from here, if our eye is here, then it will be a complete square. So, the planar area denotes this area on the screen. So, this is the area A. Magnetic flux through a plane of area A in a uniform magnetic field B. B is another concept here again. So, magnetic field is this magnetic field. The unit will be told to you in the subsequent slides. For now, to denote magnetic field we are using the letter B, capital B, and please make sure it is written here that it is a uniform magnetic field. What does uniform magnetic field means? Uniform means it is constant with time, it is not varying. At time t is equal to 0, the value of B is, let us say for example 5 units, and after at t is equal to any time t, the B value is also 5 units again, then the magnetic field is uniform. So, magnetic flux through a plane of area A placed in a uniform magnetic field B can be written as phi B is equal to B dot A. So, to be more clear here B dot A is a dot product, it is a dot vector product, and as it is a dot vector product, B dot A is equal to B multiplied by A multiplied by cos component. So, here theta is the angle between B and A. Moving on, the above equation can be extended to curved surfaces and non-uniform fields also. So, curved surfaces as you can see on the right hand side in this figure, the surface was a planar figure. The surface was a planar figure with no curves. Even if the curve was something like this, let us suppose, or even if B changes with time, the B is not B changes with time. Let me write it. B changes with time. Then by using concept of integration, we can directly find what is the magnetic flux value. Moving on, if the magnetic field has different magnitudes, the same concept which I told you just now is being put in the next point. If the magnetic field has different magnitudes and directions at various parts of a surface as shown in the figure below, the figure below corresponds to the below figure here, this figure has been talked about here. Then the magnetic flux to the surface is given as F is equal to B1 dot D1A plus B2 dot D2A plus dot means any time any n number of magnetic fields can be there with varying values, with varying magnetic field values, with varying areas. Area can also vary. So, the complete is summation of Bi dot Dai, where all stands for summation over all the area elements Dai comprising the surface, and Bi is the magnetic field at the area element Dai. Okay. Now, things to be noted about: the SI unit of magnetic flux is Weber. Please make sure that the SI unit of magnetic flux is Weber or Tesla meter squared, and magnetic flux is a scalar quantity. It is a very important thing to note it down here, that magnetic flux is a scalar quantity. So, let us move on to Faraday's laws of induction. This was a simple concept here, that to know the situation is phi b should be is a vector dot product which is equal to B into A into cos theta. Let us move on. So, Faraday's laws of induction. So, when those experiments were performed, as I already told you in the last lecture, that there were 3 experiments being performed, then several more experiments were performed as to why this is happening, what else applications can be derived from these concepts, how is it happening. So, the scientists keep on experimenting more and more stuff, and hence these more laws came into picture, or to principalize the concept of the experiments already performed in the last lecture. The 3 experiments I told you about, these laws came into picture. So, let me explain you line by line. So, Faraday arrived at a conclusion that an EMF, for now just I will explain what EMF is. For now, consider it as a voltage, consider EMF as voltage. Just to convey you, it is also known as electromotive force. So, EMF is nothing but for now consider this to be a voltage value, a voltage difference value, but it is actually a force, electromotive force. So, EMF stands for electromotive force. So, Faraday arrived at a conclusion that an EMF is induced in a coil when magnetic flux through the coil changes with time from the experimental observations. So, here experimental observations denote the experiments we conducted yesterday, or which I told you about, 1, 2, 3, and several other experiments which were being kept on being doing by these scientists. Magnetic flux here is the same concept I told you in the last slide, which is phi b. If it changes with time, that means there is a change in delta phi with respect to change in time. So, there is a change in time also, there is a change in phi also. So, this line tells that there was a change in, or due to the change in magnetic flux with the change in time, an EMF was being developed and induced is developed. It was 0 first. Induction means anything which is developed abruptly by change in something is known as induction. So, if a voltage was being induced, then the reason for that voltage induction was being told to change in magnetic flux with change in time. Next point, experimental observations discussed in previous lecture can be explained using this concept. So, this is the only line which I told you about when I was explaining the first point. The motion of a magnet towards or away from coil C1, let this be coil C1, let this be the magnet denoted by M, let this be in a circuit with a galvanometer also attached. These all concepts were being told in the last lecture. What's a galvanometer? Why does it show a deflection? What should be the direction of the current? What should be the direction of deflection of galvanometer? So now let me focus on the third point only. So the motion of a magnet towards or away from coil C1 in experiment 1 and moving a current carrying coil C2 towards or away from coil C1 in experiment 2. So what was experiment 2 being told about? That there is a coil which was C1, there was a coil which was C2. So here the movement was either of magnet towards the coil or away from the coil, or magnet being stationary, coil going towards the magnet or away from the magnet. So these were the 4 types of cases in experiment 1. Similarly, either C2 is stationary and C1 is moving towards this or going away from this, or C1 is stationary, C2 is going towards C1 or away from C1. So these were the 4 types of experiments, 4 types in experiment 2. So the third point only says that these all things is nothing but change in magnetic flux only. The concept I was telling you about, that there is a term called unit, there is a change in 0 units to 5 units. So this is that unit, that change in 0 to 5, and that change in 5 to 500 is nothing but this magnetic flux only. For now, not for now, I will write the complete thing here, that this unit which I was telling you about was nothing but magnetic flux. So the motion of a magnet towards or away from coil C1 in experiment 1 and moving a current carrying coil towards or away from coil C1 in experiment 2, change in magnetic flux is due to change in magnetic flux. Next point, a change in magnetic flux induces EMF in coil C1. The first point is being just explained again with the help of an example, and the example is the similar to the lecture 1 experiments. The change in the magnetic flux induces EMF in coil C1. It was the induced EMF. Induced EMF is, for now, consider it as voltage only V, which caused electric current to flow in coil C1 and through the galvanometer. What is a galvanometer? Galvanometer is nothing but an instrument which is used to know, or which tells us about that if there is a current in a closed circuit, it shows a deflection, and hence we can know that there is a current flowing through the circuit. A plausible explanation for the observations of experiment 3 is as follows. So now to explain experiment 3, so the reason, as I already told you, these scientists, after they know what the thing has been done, they will also try to explain, or they will also try to do more experiments to find out the explanation of these experiments. So a plausible explanation for the observations of experiment 3 was follows. Let me remind you what was experiment 3. So in experiment 3, again there was a coil C1, there was a coil C2, but this time both the coils were again, let us say coil C1 was connected with a galvanometer, let us say G, and but this time C2 was also connected to a galvanometer with a battery, but there was an additional thing. The additional thing was that there was a tapping key also involved here. So when the tapping key K is pressed, the current in coil C2 rises from 0 to maximum value in a short time. Let us say that short time is delta t. In that time, as the circuit is completed, I am explaining this C2 coil here. So when that circuit is completed, there will be a current I flowing through the circuit. Due to the current being flown in the circuit, there will be an induction, or there will be a change in the magnetic field surrounding the coil C2. Due to this change in magnetic field surrounding C2, there will be a change in the magnetic flux. Because of the change in magnetic flux, with the change in time, there will be an induction in the current in coil C1. So just everything related to all the experiments shown in the last lecture was only and only due to change in magnetic flux. If I write it big here, it is only due to change in magnetic flux with respect to time. So this is the main concept, this is the reason, this is the possible explanation for all the induction of currents. So let me just read the line. When the tapping key K is pressed, the current in coil C2 and the resulting magnetic field rises from 0 to maximum value in a short time. Consequently, the magnetic flux through the neighboring coil C1 also increases. So, due to this magnetic field will surround, and due to this, first of all at this location there was magnetic field of 0 Webers, and then it changed to, and let us say any 5 Webers. So, because there was a change in magnetic flux, it is the change in magnetic flux through coil C1 that produces an induced EMF in coil C1. When the key is held pressed, current in coil C2 is constant. So, now please understand this line very carefully as to why when the key is pressed, key is held pressed as in it is kept, we are putting it like this, and we are not changing our position. When the key is held pressed, current in coil C2 is constant. So, there is no change in magnetic flux with respect to time. The delta phi b upon delta t is equal to 0. So, because it is 0, also told in the line, let me read the line only, it will be more clear. Therefore, there is no change in the magnetic flux through coil C1 and the current in coil C1 drops to 0. So, because there was no change in magnetic flux, there was no induction of EMF. As there was no induction of EMF for now let me explain you as voltage only. So, as there was no voltage difference, hence there was no current. When the key is when the key is released, so now when the tapping key was pressed like this and we release it, the current in C2 and the resulting magnetic field decreases. So, let us say it was at 5 Weber. Let me make it clear here so that everything is visible nicely. So, I just wrote here that it was 0 first and then it went to some 5 Webers. Now, when I am releasing it, what will happen is that this 5 Weber will go again to 0. This 5 Weber will go again to 0. Again there will be a change in phi, delta phi b will exist, either positive or negative, that is not of concern right now, but it will change, and because it will change, hence with respect to time there is a change in magnetic flux. Due to change in magnetic flux there is a change in EMF or an induction of EMF. EMF for now we have understood it as voltage. Because of this voltage there is an induction of current in the opposite coil. Opposite coil as in if we are changing the magnetic flux in C1, if we are increasing or decreasing the current or are tapping the key in coil C2, then there will be an induction in C1. If we are tapping or stopping the current in coil C1, then there will be an induction in C2. So, let me complete this point. Therefore, there is no change in the magnetic flux through coil C1 and the current in coil C1 drops to 0. When the key is released, the current in C2 and the resulting magnetic field decreases from the maximum value to 0 in a short time. This results in a decrease in magnetic flux through coil C1 and hence again induces an electric current in coil C1. So, just to conclude the statement here, the common point in all these observations is that the time rate of change of magnetic flux, to write it mathematically, if any time rate as in anything with respect to time, change of magnetic flux can be denoted by delta phi b. So, time rate of change of magnetic flux through a circuit induces EMF in it. That means, due to this concept, this directly relates to an increase in voltage and hence there is an induction in current. Last point states that Faraday stated experimental observations in the form of a law called Faraday's laws of electromagnetic induction. So, there is a simple line which states what Faraday's laws of electromagnetic induction, but for now the concept I was telling you about, I will just write it in a single line. So, what actually happened was because of change in magnetic flux with respect to time, there was an change in EMF. Let us say there was a change in voltage, and because of this voltage difference there was current flowing through the opposite coil. So, for now, thank you.